Welcome to Math with Professor V. This is video lecture for section 2.5 for business calculus on logarithmic functions. Now, in the previous lesson, we studied exponential functions, and naturally we study logarithmic functions afterwards. And you might say, why? Why is that natural? I'm going to give you a one-word definition that'll hopefully clarify things. If someone asks you, what the heck is a logarithm? You say logarithms are exponents. Keep that in mind, and then we're going to build on this idea right now with the following definition, okay? So for a greater than 0 and a cannot equal 1, x also needs to be greater than 0, the following are equivalent. So we write y equals log base a of x, and that means the same thing as a raised to the y equals x. So oftentimes we'll say that this is the logarithmic form of an equation, and then this is the exponential form of the same equation. So you should be comfortable taking one form and rewriting it into the other, whichever way you may need to go. And I want you to observe very carefully here. The exponent is equal to y, right? Exponent equals y. Well, in the logarithmic form of that same equation, y is equal to log base a of x. So the logarithm is the exponent in the equation. It just allows you to isolate that exponent, and you'll see why this is going to be useful in several applications that we're going to look at, okay? And so oftentimes this is referred to as the logarithmic form of the equation, and this is the exponential form. Now, if a is greater than 0 and a is not equal to 1, then the logarithmic function of base a is defined by the following: f of x equals log base a of x for x greater than 0. It's important to keep in mind this domain restriction on all logarithmic functions. So the domain is all x's such that x has to be strictly greater than 0. If you were to write this in interval notation, it would be 0 to infinity, like that. Okay, now the properties of logarithms are simple and finite. Don't add to this list, please, and you'll be in business. I think students run into issues when they try to create new properties. So let x and y be any positive real numbers and r be any real number. And then a is a positive real number different from 1. The following are true. Log base a of x times y equals log base a of x plus log base a of y. So if you'll notice, what this is saying is when you have the logarithm of a product, you can split it into the sum of two logarithms and you break up that product, okay? This should make sense, and we could prove it, but I'm not gonna go through such tedious things with you guys. But if you think of, since logarithms are exponents, right? What's our law of exponents if you were to take a to the x times a to the y? How would you simplify that? You would add them, right? That would be a to the x plus y. So you'll see these themes pulling through. The same properties of exponents apply to logarithms because logarithms are exponents. Okay, let's look at the next one. Log base a of x divided by y is equal to log base a of x minus log base a of y. So when you have a quotient, you can rewrite it as subtraction of two logarithms, and then make sure whatever quantity was in the denominator, that's the negative logarithm. Okay, you're gonna have minus log of that stuff. Next one, very useful. Log base a of x to the r equals r times log base a of x. So basically what happens is this r gets moved to the front and multiplies in front of the logarithm. Log base a of a is 1, log base a of 1 is 0, and log base a of a to the r is r. These I'm going to talk you through in like everyday words so you can understand why they make sense. When you see logarithms, remember, those are exponents. So it's basically saying, what exponent do we put on base a to get whatever follows? So read it like this. What exponent do I put on base a to get a back? What power do I have to raise a to get a? Just the first. What exponent, when you see log, what exponent do we put on base a to get 1? it has to be 0 in order for, because remember a is not 1. A is not 1. So the only way a raised to some power is going to end up to be 1 is if that power is 0. And then here, what exponent do I put on a to end up with a to the r? Obviously r. Okay. Good. So let's practice applying these properties of logarithms. And we're going to rewrite each expression as a sum, difference, or product of simpler logarithms. Another way you might see directions that tell you to do the same exact process, they'll just say expand in one word. Boom. So here we have log base 9 of 4 times m. So I can write that as log base 9 of 4 plus log base 9 of m. And then we can simplify further because notice I can reduce 4 and write it as 2 squared. So this is log base 9 of 2 squared plus log base 9 of m. And then I can lastly bring that 2 in the front, and then I have 2 log base 9 of 2 plus log base 9 of m. Okay, so a couple things I want you to pay attention to right now. Whatever the base is, you have to write it for each of the logarithms the entire time, okay? And then your final answer is completely simplified when all exponents have been brought to the front and everything is broken up completely, okay? Good. Next one, we have log base 2 of 9 times the cube root of 5 over the 4th root of 3. Now I'm going to remind you of one of the properties of exponents that's going to help you simplify here. So if you'll recall, if you have the nth root of x, you can write that as x to the 1 over n. So we're going to do that right now and rewrite the cube root and 4th root right here. So using that rule, I can write this as log base 2 of 9 times 5 to the 1/3 over, what would we have in the denominator? Very good, 3 to the 1/4. Okay, bravo. Good. Now let's expand. Notice these are being multiplied in the numerator, so I can split them up using addition, and then I'll have minus log base 2 of 3 to the 1/4. So here we go. Log base 2 of 9 plus log base 2, 5 to the 1/3, minus, because the next one's from the denominator, log base 2, 3 to the 1/4. Okay, good. Now in the next step, I'm looking, I can simplify 9 as 3 squared. So this is log base 2, 3 squared plus log base 2, 5 to the 1/3 minus log base 2, 3 to the 1/4. And then what's the last thing you notice that we can do to simplify? Very good. Bring those exponents down in the front, all 3 of them. And then we should be done. So this is going to be 2 log base 2 of 3 plus 1/3 log base 2 of 5 minus 1/4 log base 2 of 3. And we're done. I don't know why this arrow keeps popping up. Heavens to Betsy. There we go. That's what I wanted. All right, how do we feel? Good. Now let's talk about evaluating logarithms. So log base 10 of x it's very common. In fact, it's called common log. And so it's abbreviated just log x. We don't write the 10. We don't need to. So if you see a log and there's no base written, then you need to assume it's 10. And then log base e of x, oh me, oh my, that comes up so much that we've abbreviated it ln of x, natural log of x. And e, Euler's constant, which we talked about in the previous lesson, comes up frequently in a lot of finance problems, applications, and whatnot. And so also the natural log, log base e, comes up quite a bit. All right, now those two bases are the most frequently used bases for logarithms. Most calculators have the option of doing a common log, base 10, and natural log, base e. Sometimes though you're working with a logarithm in a different base and you want to change to one of these bases. So we have a change of base theorem for logarithms, and it's as follows. If x is any positive number and a and b are positive real numbers not equal to 1, then we have the following. Log base a of x equals log base b of x over log base b of a. So change of base usually confuses students at first, but then once you kind of get the hang of it, it's not so bad. One thing I want to point out, you choose b, the new base. Okay? So basically, most of the time, you start here, log base a of x, you're going to choose b. Most of the time, we choose it to be 10 or e. Okay? And then, just notice what happens here. X becomes the argument of the logarithm in the numerator, and the base becomes the argument of the logarithm in the denominator. And then you pick whatever you want that new base to be. Okay? And the application is that if you have positive numbers a and x, and a is different from 1, and say you have log base a of x, we can change it to a natural log and write it as natural log of x. See how the x went to the numerator over natural log of a. And what was b? What was the new base? It's e. Remember, log base e, we abbreviate ln. So anytime you see ln, think, oh, that's log base e. Alternatively, we could have written this with the common log base 10. We could have written it as log of x over log of a. Okay, it's equal to the same quantity. So let's practice. Evaluate log base 5 of 30. Now, you know, in my day, the calculators couldn't do log base 5 of 30. We had to use the change of base formula. Now, some of the calculators are more fancy and you can actually pick what base, but let's just do it the universal way so that regardless of your calculator, you'll be able to compute this, okay? So log base 5 of 30, pick what new base do you want to use? I love using base e. I love natural logs. Let me tell you why. Because I like writing just script ln and not lifting my pencil or my stylus. So this is going to be ln of 30 divided by ln of 5. And then you should have like a ln key on your calculator. Just make sure you're mindful with your parentheses that you close them up before you divide and whatnot. And this comes out to about 2.113282. Well, I'll stop there, 2.113. Okay, and let's just do like a good gut check, like common sense check. Remember what I told you? Logarithm, when you read it, you say, what exponent do I put on 5 to end up with 30? So does it make sense that 5 raised to the 2.113 equals 30? Does that make sense? Well, I know 5 squared is 25 and 5 cubed is 125. So it should be closer to 2 than it is to 3, just a wee bit over 2. Yeah, that makes sense. That's a good common sense gut check right there, okay? And always do that. Don't just blindly spit out whatever your calculator tells you, you know, because a lot of the times you might catch a little boo-boo that way. All right, how do you feel? Let's solve some equations with logarithms so you can see how exactly they come into play. So logarithmic and exponential equations. Solve each equation. We have log base y of 8 equals 3 over 4. So usually what's helpful if you start with one form of the equation is to switch it and write it in the other one. So what do I mean? In the beginning of the lesson, I showed you the definition of logarithmic version of an equation versus exponential version. So this one's logarithmic form. Let's switch it to exponential. And this is the same as writing y to the 3/4 equals 8. And I'll show you something. I used to help run a tutoring center at a different school I taught at for years. And I heard one of the tutors explaining it this way, and I thought it was so cute. So if this helps you, then I'm going to tell you right now. You can think of it as the loop-de-swoop. You have y raised to the 3/4 equals 8. And they just called it the little loop-de-swoop. So y, that's the base. The baby number at the bottom is the base. Raised to the 3/4 equals 8. And then 3/4 is your logarithm, right? Log equals 3/4, so that should be the exponent. Hopefully that helps. Okay, from here, let's just focus now on getting y by itself. So how do I get rid of this 3/4 exponent? I raise both sides to the 4/3. You raise both sides to the reciprocal of the exponent. because when we simplify in the next step, I'm going to multiply these by each other. Everything will cancel and just give me 1. So I have y to the first, and then 8 to the 4 thirds. That's the same thing as cube root of 8 raised to the 4th. So whatever the denominator is, you take that root of the number, and then you raise it to the numerator. So cube root of 8, that's 2. 2 raised to the 4th, 16. Okay, is that possible? Yeah. We just have to make sure y is not 1 or negative. That's fine. I'm going to put it in a little solution set. There's my answer, 16. Okay, you don't have to always use the solution set, but I was so trained to that I feel naughty when I don't most of the time. Okay, let's move on. Log base 4 of x minus log base 4 of x plus 3 equals negative 1. So how is this different than the last one that we did? Anytime you have a new equation and you're kind of freaking out, just think, well, I did solve one successfully just a minute ago. What is so different now? I have 2 logarithms instead of 1 on the left-hand side. That's the only difference, really. Do we have a way we could combine them so we only have 1 logarithm? Yes, we have a log property. Before we were expanding, right? We were breaking up into multiple logarithms. We can go the other way around and combine these into a single logarithm. Since there's subtraction going on, I can write this as log. You have to keep the base 4. You're only going to write 1 log this time, and you have x over x plus 3. So the argument from the negative logarithm goes in the denominator, and then the argument from the positive logarithm goes in the numerator. Okay? And this is all equal to negative 1. Now we can do the little loop-de-swoop. So you can write 4 to the negative first equals x over x plus 3. And then 4 to the negative first, I would just rewrite that. That's 1 over 4 equals x over x plus 3. You can cross multiply now. So 1 times x plus 3 equals 4x. So let's just leave the 3 here. 3 equals 3x, so x equals 1. And then remember when I first showed you our logarithms, y equals log base a of x, and we said this was f of x. The domain was that x had to be greater than 0. So make sure when you get a solution, you go back to the original equation and you make sure if you plugged in that value for x that both the arguments on the logarithms are positive, and they are. So we're good. So then we can go ahead, let's put it in the solution set with a clean conscience, you know, it checked out. So for example, if we had gotten 0 or a negative number, it wouldn't have worked here. So I would have had to throw it away and then just say I had no solution. So sad. Okay, let's try a few more. Next one we have natural log of x plus 1 minus natural log of x equals 1. This one's kind of similar to the last one. Why don't you pause the video and try it on your own? I have faith in you. Okay, did you combine the 2 logarithms on the left-hand side? Good, that's how you're supposed to start. So you have natural log x plus 1 over x equals 1. And then you want to rewrite this in exponential form. But if it's too aggressive for you to just jump straight there, you can rewrite this as log base e of x plus 1 over x equals 1. That's totally valid if you want to do that first. Then we can do the loop-de-swoop, right? E raised to the first equals x plus 1 over x. So e to the first equals x plus 1 over x. What would I do next? I'd multiply both sides by x. Okay. So we have x times e equals x plus 1. Oh, this is kind of funky. The x is on the left and the right. What do? I put them on the same side of the equation. Whoever you're trying to solve for, they all belong together. Everybody that doesn't have an x goes on the other side. And now I can factor it out. So I have x times e minus 1 equals 1. And then lastly, divide by e minus 1. So x equals 1 over e minus 1. Now, I want to make sure that that's not something negative, that I can go ahead and plug it into the original equation and not get something that's undefined. So 1 over e minus 1 is approximately, oops, I thought I was writing with a pen and I wasn't. It's approximately 0.58. So we're good to go. E is 2.7-ish anyways, so there was no chance this was going to be negative, but it's always good to be safe. So I'm going to put my final answer. I'm going to use the exact form, 1 over e minus 1. They didn't ask us to round or anything. I just did that for us to make sure everything was good to go. Okay? Very nice. Next one, we have 5 to the x equals 12. So this equation's in exponential form. I don't see any logarithms. And unlike the exponential equations in the previous lesson, I can't write both sides in terms of the same base. I don't know if you remember, but like last time we had 5 to the x equals maybe something like 25. So we wrote it as 5 to the x equals 5 squared, and then you could just say x equals 2, easy peasy. But that's not going to happen here because there's no way I can write 12 as 5 to the something, right? So we're stuck. The old method isn't going to help us. So what we do instead is we take the log of both sides, or you could take the natural log of both sides. So let's write that out. So natural log of 5 to the x equals natural log of 12. And why are we doing that? Well, now I can use my log property and move this exponent in the front. So now I can write the left-hand side as x times natural log of 5 equals natural log of 12. Ooh, and then to get x by itself, all you have to do is one little maneuver. That's right, you just divide by ln of 5. Boom. Shall we see what it is? Now, there's no restrictions here because this original equation is an exponential equation. So, I mean, it could be positive, it could be negative, doesn't matter. I mean, just if we want to do like common sense check though, it's approximately 1.544. So does it make sense? 5 raised to the 1.544 is 12. I mean, it's got to be more than 1 and less than 2. Sure, I'll buy it. Sounds good. For your answer though, when you report it, just always do exact unless you're instructed otherwise. So like if it doesn't say round to 2 decimal places, then nobody wants your decimal answer. You just give this one. This is the exact one. This is crooked. I don't like it. Hold on. Oh, much better. Okay. Same idea for E. It's just the spice level has been increased significantly. Are you ready? Okay. Starting off, we're going to take natural log of both sides. So we have natural log 2 to the x plus 1 equals natural log 6 to the x minus 1. Next step is same as the last problem. You move those exponents in the front, but just please be careful. Keep parentheses around them. So write it as x plus 1 ln of 2 equals x minus 1 ln of 6. Does that make sense? Oh, good. Okay, now things are going to get worse before they get better. We want everything that has an x on the same side so we can factor it out like we did a couple problems ago. But before we can start moving things around, we have to distribute. Okay? So we're going to write this out as x times ln of 2 plus 1 times ln of 2 equals x times ln of 6 minus 1 times ln of 6. And then now the terms that have x's need to be together. They're so lonesome without each other. So we're going to put them on the same side of the equation, and everybody that doesn't have an x gets exiled to the other side of the equation. So we have x ln of 2 minus x ln of 6 equals negative ln of 2 minus ln of 6. Oh, we're almost there. Now I can factor out an x from both these terms. So I have x times ln of 2 minus ln of 6 equals negative ln of 2 minus ln of 6. And then lastly, I'm just going to divide by ln of 2 minus ln of 6 on both sides. So final answer, actually JK, we're going to clean it up more. Negative ln of 2 minus ln of 6 over ln of 2 minus ln of 6. Now, I'll show you how to clean it up. We're going to take a negative out of the numerator. So it'll be ln of 2 plus ln of 6 once I've factored it out over ln of 2 minus ln of 6. And anytime you reverse the order of subtraction on a quantity, that changes the sign. So that multiplies by another negative. So I can switch this. This is equal to negative ln of 6 minus ln of 2. And then these two negatives would end up canceling each other out. So the most cleaned up final answer would be ln of 2 plus ln of 6 over ln of 6 minus ln of 2. And then, I mean, why stop there? We can combine the logarithms in the top. Ln of 2 times 6 is 12 over, this is ln of 6 divided by 2 is 3. Yes? Yes. Should we stop there? I think so. Okay. So that concludes the lesson. If you wanted to do change of base, you could write it as log base theorem of 12. I mean, we got to stop at some point though, so I think that's good. Okay. If you want to plug it in the calculator, you can. We're just going to leave it there for now. So that concludes the video. Give it a thumbs up if you found it helpful. Subscribe to the channel if you haven't already. And coming up next, we'll look at some more applications where we're going to use logarithms in our interest and finance problems. If you need help reviewing any of the topics that we covered, or you want more video lectures on logarithms and whatnot, I'll link some of the pre-calculus ones. But again, if you're a business calculus student, some of the pre-calc problems are more intense than what is needed for this specific course. But if you're just learning for pure enjoyment or just as a review, then I have a lot more resources for you. Also, you can follow me on Instagram, TikTok, Twitter, Math with Professor V. I love you so much, all of you guys, each and every one, and I'll be back sooner than later. Bye!